Okay, we are going to start now talking about deoxidation, ladle and tundish metallurgy operations. However, before I start talking about these topics in details, let us quickly go through the section of primary steel making, and then the relevance of secondary steel making or the deoxidation, ladle and tundish metallurgy will be clear to you. Now, for example, we have this BOF vessel in which is a refractory lined vessel with one lance, and we have molten metal here, and after say about the duration of oxygen injection, when the end blow period is over, what we do, we typically, so this is the half of the furnace, okay, and we have the tapping hole here, and we have a ladle here, and the tapping streams as this furnace is being tilted. So the metal builds up in this ladle. This is my BOF, which is, I am showing only one half of it with the line of symmetry here, and this is again to show that the vessel is refractory lined. So the inevitable consequence of primary steel making, as this metal is going to be nearly saturated with oxygen. Okay, so we have lot of dissolved oxygen in the melt, and once decarburization is completed, we have to take it out in order to first remove the dissolved oxygen, because we know that oxygen dissolved in steel is going to seriously impair the properties of steel when molten steel will be converted to solidified products such as billet blooms and other shapes. So this is true not only of a BOF, basic oxygen furnace. BOF stands for basic oxygen furnace, as you all know, but it is equally true of other oxygen steel making or electric arc furnace processes, where we inject oxygen, and as a consequence of the refining reactions, we have lot of dissolved oxygen in the melt. Now, at this particular point, I will try to classify steel making under two different processes, and I will say chemical processing, chemical and physical processing, and number two is transfer operations. So the steps that we carry out in a BOF vessel or an electric arc furnace or an oxygen steel making converter such as an EOF, energy optimizing furnace, we will classify those as chemical and physical processes, where we change the composition. On the other hand, when oxygen steel making process is over, we have to tap the molten metal into the ladle. This particular process we are going to call it as a transfer operations. As we will see during the secondary steel making, that transfer operations are also equally important, as does the physical and the chemical operations carried out in the primary steel making vessels. So the objective of primary steel making, as we have seen during earlier lectures, is to primarily decarburize the bath, because once we wish to take out many other aspects of steel making, for example, composition adjustments, temperature adjustments, then unnecessarily the duration of the blow is going to be substantially large. So today the tendency in modern steel making companies is that use this vessel only for decarburization, and subsequent operations like maybe desulfurizations or composition adjustment or temperature adjustments can be carried out in a vessel which is beyond the primary steel making vessel, and there we will see as we advance that the ladle will be evolved into a very useful reactor, which we will call as the ladle furnace. So having made the steel of the correct composition, say we started with pig iron, which has 4% or 4.3% of carbon, and now we have blown oxygen through the lance into steel, as a result of which the steel which is coming into the ladle does not contain much of carbon, but as a consequence of this oxygen injection, it contains a lot of dissolved oxygen. And we got to remove this dissolved oxygen. We must remember that as we tilt the furnace, rotate the furnace to tap the content of the BOF into the ladle, what is going to happen is that there will be a possibility to entrain the slag, because we have generated lot of slags also here if you remember. So, these slags are also can be entrained as we tilt the furnace, to drain out most of the material. So, this slag which is going to come inevitably along with molten steel are going to be termed as the carryover slag. This slag is a highly basic slag, contains silica, and most importantly, because of a large amount of oxygen injection, this carryover slag is going to be rich in dissolved oxygen, or its iron oxide content is going to be very, very large. Depending on the process, we can have approximately 20% iron oxide in the slag itself. And mind it, this slag has a highly oxidizing slag. Its oxygen potential is very, very large. We are not going to entertain any amount of this slag coming here, because we are now going to remove oxygen, which is essentially a deoxidation or reducing operation itself. So, the carryover slag, as we advance, we will see, influences adversely the properties of the steel. So, as a result of which, all subsequent refining reactions beyond the primary steel making vessels, which are going to be carried out in a ladle, are actually going to be used in the presence of a new slag. We must remember that we would like to have some slag here, but this slag is not going to be the carryover slag. This slag is going to be a fresh slag, which will be devoid of any iron oxide as such. So, we may add some to start with when the ladle is empty. We can start some lime, we can add some fluorspar, we can add some silica, and as a result of which we can form a fresh slag which may float on top of steel, because the slag, as you all know, is lighter than steel. And as this slag floats on top of steel, what happens is that it provides a protective cover over the steel. So, it is not going to be in contact with the atmospheric oxygen or nitrogen. Similarly, the heat will not be able to escape. Q will not be able to escape through this slag layer, because which is going to act as a thermal insulator over the bath itself. But this slag, I would repeat again, is not the carryover slag, not the slag from the basic oxygen furnace, but it is the slag which is made afresh in the ladle. So, initially we will have the ladle which is empty. Then as steel is made, or decarbonization is completed, we will tilt the furnace or the basic oxygen furnace, and then tap molten metal. And as molten metal comes into occupy the ladle, we are now going to see that there is going to be extremely large amount of recirculation which is going to be produced as a result of molten steel impinging. This is just like the way, for example, if you take a bucket in your bathroom, open the tap, and then that is the kind of a filling operation that basically goes on here. And as you can see that, or witness, I would request you that you go to the bathroom, take a bucket, open the tap, and observe for yourself how the bucket gets filled up, and that is precisely the scenario that one would see in the case of the ladle filling operation. If you take a plastic transparent bucket, you possibly can see in the bathroom air entrainment. So, you will see lot of oxygen, sorry, not oxygen but nitrogen, because the material is already saturated with oxygen. There is not much concentration gradient between the dissolved oxygen or the oxygen potential in the atmosphere and here. So, as a result of which there will be no oxygen transfer between the molten metal and the ambient. On the other hand, you have lot of nitrogen gas here. We can have some nitrogen and hydrogen which can be absorbed by the tapping stream, and you will see, or one can see really, that there is lot of air entrainment. What happens is that when this jet, which we say is an impinging jet on the surface of the ladle, it strikes the ladle, then it moves in a counterclockwise direction, and as a result of this rotation, it is a very extremely high speed of rotation. So, whatever we have added here to make the fresh slag, they get dissolved or melted very quickly and instantaneously, possibly we are going to have. So, we must understand that during the tapping operation, an extremely intense hydrodynamic stirring is available in the bath itself. So, now if you are going to add some elements which are going to react with the oxygen in order to take away the oxygen from the bath itself, those elements can melt and dissolve in steel very quickly. For example, if you add a drop of potassium permanganate in that bucket, on which you can do an experiment in a bathroom, you can see that the potassium permanganate will dissolve in the bucket of water very rapidly, and same happens in steel making ladle also during the furnace tapping operation. So, refining is far from being complete in the primary steel making vessel, and that is why there is a need for many subsequent operations or an entire ladle metallurgy treatment stations in steel plants to adjust the composition and temperature of steel. And I say repeatedly say temperature and composition. Composition is to meet the demand of the customer, and temperature because this there is a stringent requirement on the part of continuous casting that the metal be delivered into the continuous casting mill, continuous casting mold at the right amount of superheat. So, as primary steel making is over, we can assume that there is going to be maybe sulfur, which is more than the required specification. Although we would like to have now phosphorus absolutely in the right level, I must also mention here that there is an increasing trend that for high phosphorus steel that we are going to have some kind of a pre-treatment, which you of course have done. That between blast furnace and primary steel making, we have pre-treatments like desiliconization, desulfurization, and we are building up gradually dephosphorylation as well. So, we can have lot of sulfur in the basic oxygen furnace, and we know why sulfur is going to be there, because the conditions in basic steel making furnace of BOF is not conducive for the removal of sulfur, because removal of sulfur requires a basic and reducing environment, and that is why in primary steel making, which is an oxidizing process, sulfur removal is not facilitated. We have to carry out sulfur removal under a reducing condition, as we will see later on. So, we can have lot of dissolved oxygen also, and maybe because of the transfer of nitrogen, as I am saying, that the material which comes may have lot of dissolved nitrogen and hydrogen also. And all these things must be adjusted, the composition, and also we may remember that we may not always want a plain carbon steel. There may be a demand for alloy steel, etc. So, we have to make some alloying additions into the ladle also in order to get to the final desired composition. So, these are unwanted elements which are present beyond the primary steel making vessel, primary steel making reactor or vessel, and these have to be eliminated in the secondary steel making process or in ladle metallurgy treatment. We must understand here that the capacity of a ladle is identical to the capacity of a BOF or an electric arc furnace. So, if it is we are talking of 130 ton capacity, we are going to have 130 ton capacity for the ladle also. There are going to be innumerable number of ladles in the plants, and the ladles are typically recycled, because this ladle which is below the oxygen steel making furnace will be moved from the steel melt shop to the ladle metallurgy station, where we may carry out a host of treatments or a variety of processes, including tank degassing, ladle furnace to raise the temperature, composition adjustment, gas stirring, etc. And finally, the ladle will be placed over the turret in the continuous casting mill, and where it is going to be casted. And as the ladle over the continuous casting mold is going to be emptied, it is going to be recycled back and brought under the primary steel making furnace, and this is called the recycling of the ladle. That from here it goes to the continuous casting bay, and from the continuous casting bay an empty ladle comes, and so a ladle is going to be used for a number of hits before relining is going to be necessary. But typically we must understand that the capacity of the ladle and capacity of the furnace are going to be identical. One hit is going to be poured in one single ladle itself. To summarize in this particular section, so before we proceed further, we must remember that we do not want oxidizing slag to be present in ladle, we want fresh slags. And to start with, we must remember that the metal which comes here contains lot of dissolved impurities, and these have to be driven out. And also we must remember that there is going to be an intense agitation which is going to be built up in the system because of the incoming jet of molten metal from the BOF. But we must also understand that as the metal is going to be emptied from the BOF, then eventually this intensity of motion here is going to die down, because at some point of time this is completely emptied, so there is nothing is coming out, so there is going to be not sufficient amount of stirring. So that is why the moment we start to pour molten metal, we will see that we have a porous plug which is located here at the bottom, through which we are going to inject argon. So, even when the intensity due to the impinging stream will die down, this gas or argon which is being injected through the porous plug will give rise to a reasonable amount of stirring in the system. We want stirring in the system because, as we know, steel making reactions are basically mass transfer control. So, therefore, unless we have good amount of stirring, okay, the mass transport of mass from one point to another point is not going to be aided. So, therefore, to facilitate various steel making reactions or moving of heat from one point to another, we have to have some amount of stirring present, and gas stirring, by the way, is the cheapest mode of ensuring stirring in a high temperature system, which is at 1600 degree centigrade. We can see that when the material is completely filled, okay, or before the material is completely filled actually, as the furnace, basic oxygen furnace is being emptied, we are going to continuously now add deoxidizer elements into the steel bath. Now, we have to eliminate, the first step is, as I mentioned, is to drive out this oxygen, and this is called deoxidation of steel bath. And to deoxidize the steel bath, we basically add elements which have greater affinity for, or very high affinity for oxygen. So, what we can do basically, we can just, as the ladle is being filled up, okay, with a stream, we can drop deoxidizer elements in bulk form. You can go to the steel plant and see that aluminum bars of this sizes are going to be poured into the molten steel. And also I said that we can, you can use other kinds of deoxidizer elements also, and commonly used elements in addition to aluminum are ferrosilicon, ferromanganese, silicomanganese, etc. So, aluminum, ferrosilicon, ferromanganese, silicomanganese, these are commonly added deoxidizers in steel bath, and these additions including aluminum can be made in lump forms. So, you can take solids or in powdered forms. Again, if you take powder forms or small particle sizes, we can understand that their melting and dissolution is going to be very, very rapid because of the larger surface area. So, as the bath is being filled up, we can keep on adding. Typically, if you go to steel plant, you will see that gunny bags filled with ferrosilicon, ferromanganese, etc., are being continuously dumped into the ladle, and this doesn't have too large a melting point. So, therefore, they melt and dissolve very quickly into steel, and once they dissolve into steel, what happens is the reactions between oxygen and the dissolution and the dissolved species sets in. Now, we must understand before we proceed to discuss deoxidation that these are cold elements. They are staying in the steel company yard at some places, in some godowns, and these are basically at room temperatures. On the other hand, when we add them into the steel bath, what is going to happen? Their temperature is gradually go up. They have to melt because we have the dissolved oxygen in steel. So, these solids will not be able to react with the oxygen present in steel unless this also dissolves. So, we have, for example, aluminum which is in solid form, and then this aluminum becomes in liquid form. So, aluminum melts because of, and this liquid aluminum basically, then what happens? It gets dissolved in. Once aluminum gets dissolved into steel, it can now see oxygen, and as a result of which aluminum and oxygen can react. So, before actually the deoxidation reaction, which is generally represented like note that a third bracket essentially implies that it is dissolved in steel. A first bracket, on the other hand, it talks of a different phase, and we say that it's an oxide phase, basically the slag phase. Okay, it is also written like the dissolved state is also written like if you write the reaction, it essentially tells that it is a forward reaction. But if you wish to consider the reaction operating close to equilibrium, in that case we would say that we raise this, we write it like this, which tells us that the reaction is operating under reversible condition. It is about to reach or operating close to equilibrium itself. And this deoxidation equilibria we are going to study in great detail. But before this reaction, as I have mentioned to you, can take place really, we have to have, M, for example, here if it's aluminum, then solid aluminum I have added, the solid aluminum has to melt, the solid aluminum has to dissolve, and then there can be reaction between dissolved aluminum and dissolved oxygen. So therefore, we must understand the interactions, thermal and physical interactions between the solids as well as the added solids as well as the oxygen itself. So the solid initially at room temperature, as it is projected into a liquid bath, typically what happens is that we have a solid shell which forms around the initial solid. So this is the crust. So therefore, if this is aluminum, we can expect that the crust material is essentially the bath material. So this is going to be actually steel crust. Now, what sort of a thickness of crust is going to form? That will basically depend on the bath temperature, depend on the size of the addition, depend on its specific, and there are a lot of other physical properties on which the extent of the solid crust forms. But nevertheless, it is a well-known fact that when a cold solid is projected into a hot bath, like aluminum projected into steel, we are going to have a steel crust around the solid. Now, typically what happens is there are two possibilities now, that within the crust itself, we can have the aluminum already melted. This is one possibility, and this we say is aluminum, and this is the solid crust. And the other possibility is that we can have that the solid aluminum is going to be released, the crust melt backs, and the solid aluminum is, so the crust melts back, and the solid aluminum is released. So these two possibilities will again depend on the bath superheat, etc. But in any case, what happens is that from this, the aluminum, if it happens like this, then the aluminum will become again aluminum liquid, which I will say, and then we can see that it is going to go to aluminum in the dissolved state. So these are basically the way a solid projected into steel is going to behave like. Now, this particular step I would like to draw your attention to can only happen provided the addition has a melting point which is lower than the bath temperature itself. For example, if I add an addition like ferroniobium, of course I am not going to add ferroniobium to deoxidize the bath, but just to mention in this context that if I add ferroniobium, which is a melting point greater than that of the bath temperature of steel, which is about 1600 degrees centigrade, so ferroniobium actually will never melt in steel. Ferroniobium will dissolve in steel. For example, if you add sugar to a pot of tea or a cup of tea, the sugar does not melt in tea, the sugar dissolves in tea, and dissolution is a mass transport step, melting is a heat transfer step. So those additions which has melting point greater than the bath temperature will not dissolve, and they are typically said that these are the class 2 additions, and the class 2 additions have T2, T melting point 2 is greater than actually T bath, and this T bath is what we are talking about is 1600 degree centigrade. On the other hand, deoxidizer elements are called are basically class 1 type of additions, class 1 additions, and the feature of the class 1 additions is such that T melting of class 1 is less than T bath. So therefore, we can understand that this class of additions or the deoxidizer additions are going to melt in steel, ferrosilicon, ferromanganese, etc., and we are going to or aluminum. On the other hand, if you are talking about for example ferromolybdenum, ferromolybdenum, then ferrovanadium, then ferroniobium, etc., this type of additions are going to really not melt but dissolve into steel because their melting points are greater than steel. But these features of formation of crust will be observed everywhere, and then finally the melting, through melting dissolution, we are going to have the material in the dissolved state, and it is under this dissolved state that an interaction with oxygen is going to take place, and as a result of which the oxygen from the bath is going to be continuously decreased. As we see that more and more metal oxide is going to form, or the oxide is going to form, the less and less oxygen is going to remain in the bath itself as the reaction is being driven forwardly. We also must realize that the solubility product principle tells us that if the activity of the oxide is going to be smaller and smaller, this reaction will have a tendency to move into the forward direction. And therefore, if we have some kind of an oxide to stabilize the deoxidation product, we can take this deoxidation reaction in the forward direction in a much more efficient manner. Now, what sort of an element, why we add this kind of an element like aluminum, ferrosilicon? One feature is that we must realize that silicon, aluminum, manganese, etc. have very high affinity towards oxygen. Now, in terms of their capability to remove oxygen, I would say in descending order it goes like carbon also has good affinity towards oxygen. So, but we don't want to add carbon to deoxidize the bath, because we have already struggling hard to remove carbon during the oxygen steel making processes. So, this is not ruled out as a potential deoxidizer in the case of steel making. Now, these elements have great affinity towards oxygen, and where from we know these things? We have seen the oxygen Ellingham diagram. In the Ellingham diagram, which is a plot between delta G naught and temperature, okay, and there we have seen that the aluminum, okay, if line is here, and then we see we have a silicon line here, and then we see manganese line here, and carbon line even above. Lower is the position of the line in the Ellingham oxide Ellingham diagram, greater is the stability of the oxide, or greater is the affinity of the element towards oxygen. We can also say that if the affinity towards oxygen is higher, so therefore the residual level of aluminum for a given oxygen is going to be less in the bath. So therefore, the contamination of the bath as a result of deoxidation, if I say that the final oxygen is fixed, then I can say that on the basis of this information I can conclude that the residual level of contamination with aluminum is going to be lesser in comparison to silicon, in comparison to manganese, and these we can immediately, these conclusions we can immediately draw from the oxide Ellingham diagram, and that's why in the study of carbothermic reduction, in the study of deoxidation, the Ellingham diagram occupies a preeminent position. We have to know this really well. So we would like to have a deoxidizer element. That element must have a great affinity towards oxygen, and then we are going to add, and then we find that the most commonly used deoxidizers, which are also easily available. We must understand we don't add pure manganese, we don't add pure silicon. They are added in the form of ferrosilicon, ferromanganese, because technologically it is far more advantageous to make ferrosilicon than pure silicon, as we all know, or ferromanganese than pure manganese. So therefore, ferrosilicon, ferromanganese, silicomanganese, aluminum are the potential deoxidizers because of their higher affinity towards oxygen. Okay, now this shows the bulk addition of the deoxidizer elements like aluminum, etc., as we are talking about. And one property I think you should have been able to register by now is that these deoxidizer elements like ferrosilicon, silicomanganese, aluminum, they are much lighter than that of steel. Okay, their density is much lighter than the bulk steel. So therefore, the deoxidizer elements, okay, when they are added, and lighter includes aluminum, ferrosilicon. Ferromanganese has the same kind of silicomanganese. Ferromanganese nearly can, depending on the grade of ferromanganese, how much percentage of manganese you have in that, you can have almost neutrally buoyant. That means almost same density as that of steel. Manganese and iron, they are close in the periodic table, so their properties are similar. They form ideal solutions. Their densities are similar. So ferromanganese also has, depending on how much of manganese you have, may have the same type of density as that of steel. So these deoxidizer elements are basically lighters, and when you are trying to pour them into the steel bath, it is understood that these deoxidizers will not penetrate much deeper into the bath. Okay, for example, go to a swimming pool, take a ball, and you try to submerge the ball into water, underwater. Suppose you force the ball with extreme speed on the surface of water in the swimming pool, what did you see? That the ball does not really penetrate much, because the density of the ball is substantially smaller than the density of the bulk water itself. So, even though the deoxidizer element is falling from a height of 3 to 4 meters in a typical steel melt shop, these deoxidizer elements are going to hardly go subsurface. So, they are going to remain mostly near the free surface itself, or free surface means the surface of the steel itself. And that is why if you visit a steel plant next time, take note of it, that these lighter deoxidizer elements are going to be thrown in the vicinity of the impinging spot where the impinging stream is actually entering, because it is in the vicinity of the impinging stream that we have an extremely large downward motion, and we want these additions to be captured by this downward motion and drawn inside the bath, because we don't want the deoxidizer elements to react with the environment. Okay? No, I don't want my aluminum to be reacting with oxygen which is present in the atmosphere. I want my aluminum to react with oxygen which is present in the steel bath itself. So, therefore, my objective would be that you add the deoxidizers in such a way that the deoxidizer has some potential to go below the surface of the steel, where it can melt, it can dissolve, and then it can react with oxygen which is present in the metal itself. And the most important site as far as their entrainment or their motion in subsurface is concerned is the region, which is close to the impinging jet region, where you have a largest downward motion of liquid steel. And if these additions can be caught in this particular region, then they have a potential to spend substantially longer time under the bath, and their efficiency of utilization is going to be larger. As the deoxidizer elements get inside the bath, they melt and dissolve, react with oxygen, slags form, and I have shown with colored chalk here that the formation of the slags, simultaneously the stirring goes on, and because what we did, the mass transfer reactions, we always want that the oxygen and metal must come in contact with each other, and then only this product is going to form. So, we want to create a kinetically favorable condition. We want to create some stirring all the time, such that oxide is transported from one place to another place. Okay, from this part to this part, the oxides are always lighter. That is why the oxides of the slag is going to float up, and the amount of the slag is going to be progressively building during the process of ladle filling operation as well as deoxidizer element addition. So, deoxidizers upon their entry into the bath will spend some time subsurface, and then in the process of that they are going to react, they are going to dissolve, melt and dissolve, and react with the bulk steel oxygen in the bath steel. So, this we say is the deoxidation product. And if we assume that the deoxidation product is in pure state, okay, so that means there is no compound formation here. If aluminum is projected, aluminum reacts with oxygen and pure aluminum forms. There is no calcium aluminate or aluminum silicate, etc. No other phases are present. In that case, we can consider that this is going to be activities of the deoxidation product is going to be 1. And if we write down under equilibrium, if we assume that the reaction is under equilibrium, because we want to study the thermodynamics of the deoxidation process first, we can say that the K equilibrium is going to be equal to activity of the metal oxide Mx Oy in the slag, okay, and then activity of metal raised to the power x and activity of oxygen raised to the power y. For the time being, taking the case of a pure deoxidation product, we can find out that activity of metal is going to be in the bath is going to be inversely proportional to. So, therefore, lower and lower oxygen we wish to achieve, greater and greater is going to be the activity of oxygen or the activity of metal or activity of concentration of metal in the bath itself. So, for example, if you use aluminum, okay, and your final, suppose you decide that your final level of oxygen you want is 50 ppm. So, then you get a residual amount of oxygen, residual amount of aluminum, say 0.02%. I am just arbitrarily quoting a figure, okay, for 50 ppm final oxygen. Okay. Now, if I say that if you want to get to 10 ppm, okay, in that case this value is going to be smaller or larger. This value is going to be substantially larger than this because of this particular relationship, that the activity of oxygen, the activity of oxygen is inversely proportional to activity of metal in the bath. Lower and lower is the concentration of oxygen you wish to achieve in the bath itself. So maybe, to be consistent, at least to show a realistic value, I would say that it will go up to this level. These are not exact values, you have to calculate it out, but I just want to show the trend that if one goes down, the other goes up, and this is as a result of the consideration of the deoxidation equilibrium. So this is at a given temperature. When there is equilibrium. Now this deoxidation product need not be solid all the time. The deoxidation product could be liquid also, and under extreme cases, if you are using carbon to deoxidize the bath, just a hypothetical situation, of course, in that case you have a deoxidation product which is a gaseous deoxidation product, carbon monoxide or carbon dioxide, depending on what condition and oxygen potential you have in the system. Okay, so deoxidation products need not be solid all the time. We can write deoxidation product can be solid, liquid, and gaseous. Okay, and we can have liquids. Liquid deoxidation products are basically compounds, as we'll see later on. Solid deoxidation products, as I have mentioned, alumina you can visualize as a solid deoxidation product, and then gaseous deoxidation product is when you add carbon monoxide. Now the amount of deoxidizer required in steel melt shop is a very important information that one would like to say, that I started, for example, with 2000 ppm of oxygen in the bath. Now I want to get to 20 ppm of oxygen. I want to add aluminium, and can you now tell me that how much of aluminium really I would be adding to the steel bath itself? I have a vessel size of 150 ton, for example, is the ladle size. Okay, initial oxygen from the basic oxygen furnace is 2000 ppm, final oxygen is 20 ppm, and then I wish to add aluminium in that 150 ton ladle. Now I want to know that how much of oxygen aluminium I should be adding in order to achieve a final level of oxygen, or a net reduction of 1800 ppm of oxygen. So how do you do this kind of a calculations? We must understand that there are two requirements which the deoxidizer has to fulfill, and one is called the stoichiometric requirement, and the other is the thermodynamic requirement. What do I mean by stoichiometric requirement? That you have, if you did, for every 16 grams of oxygen, you are going to need 27 grams of aluminium. Straightforward calculation. This is the stoichiometric requirement. So I know that 1800 ppm oxygen is to be eliminated, and this 1800 ppm oxygen with respect to the 150 ton ladle size can be translated to so many kg of oxygen. Then by using this relationship that 16 kg of oxygen will require 27 kg of oxygen, I will be able to immediately calculate that how much of oxygen is going to be required in order to reduce the total amount of oxygen which is present, oxygen which is present in the bath corresponding to 1800 ppm. And this I say as a stoichiometric requirement. 16 grams, I will write it for you. 16 grams of oxygen needs 27 grams of aluminium, and on the basis of this you will be able to carry out. So beyond this stoichiometric requirement, we have another requirement to fulfill, and that is the thermodynamic requirement, because I mentioned to you that for a given level of final oxygen there is going to be some equilibrium aluminium content or deoxidation content in the bath itself. So we have to find out that, well, one part of aluminium which has reacted with oxygen and has gone into the slack phase. Okay, the other part of the oxygen which is lying in equilibrium, and which remains in the dissolved state, which has to be calculated on the basis of this particular expression. Now, as I said, if I assume for the sake of simplicity that the metal oxide is in pure form or alumina is in pure form, there is no other oxides present, I can set that activity of this is approximately is equal to 1. I can obtain the value of the K equilibrium because I know that delta G naught is equal to minus RT ln K equilibrium, and therefore, using the value of the gas constant, okay, the right temperature, and because I know the value of delta G naught, okay, at various temperatures. And how do I know? Because this is tabulated in thermodynamic data books. Many people have done experiments and have determined this data. So, therefore, determination of data is a very important step for us, particularly when we evolve new systems. Okay. So, knowing the value of delta G naught, I should be able to calculate that what is the value of K equilibrium. So, if I know the final level of oxygen in the bath, and that final level of oxygen is 20 ppm, of course, this is to be written in appropriate scale here. I can use a Henry activity wet percentage scale, or whatever comes out to be convenient. Typically, the wet percentage scale suffices here. So, if K equilibrium is known, this is equal to 1 for the given value of activity or concentration of oxygen, I will be able to find out that how much aluminum is there in equilibrium, and I can translate that much aluminum with reference to 150 ton bath and say that, well, 4 kg of aluminum is there, in the dissolved state. So, if I say that 10 kg is required as far as this stoichiometric, stoichiometric of the reaction, stoichiometry of the reaction, in that case I can say that add this with the thermodynamic requirement, and that is going to be your total requirement. So, you have to add that much of aluminum into the bath in order to reduce the initial 2000 ppm oxygen to the 20 ppm. So, this is a very important calculation which the melt shop people as well as you all should be able to carry out, without much hiccups. Deoxidations basically are two types. One is called the simple deoxidation and the other is called complex deoxidation. Now, what does this imply? The simple deoxidation means that you have only one element, and complex deoxidation means we have more than one element. More than one element. So, therefore, if I say that I have added aluminum or ferrosilicon, I will say that, well, aluminum is deoxidizing the bath or silicon is deoxidizing the bath. I am not adding them together. I am adding just one of these, for example. So, if I add one element to deoxidize the bath, I am going to say it is a simple deoxidation. If I add more than one element, for example, what is this? Silicomanganese. So, some oxygen is going to be eaten up by silicon, some oxygen is going to be eaten up by manganese. So, I am adding silicon and manganese simultaneously into the bath in the form of silicomanganese. I am going to say that this is a complex deoxidation. Typically, the efficiency of complex deoxidation is far more than simple deoxidation. And why it is so, you should be able to understand. For example, if you look at the product of deoxidation, as I mentioned to you, it is, and I mentioned to you that smaller is the activity of this product of deoxidation, better will be the possibility of the deoxidizer reaction to go from the left to right. Okay? So, metal will combine more efficiently with the oxygen itself. Now, in the pure form, okay, if the oxide is pure, then activity of MxOY is going to be is equal to 1. On the other hand, suppose the deoxidation product is silica, and then I am adding some lime into it. So, the lime and silica are going to combine with each other. Okay? So, in a pure silica melt, silica rich melt, the activity of silica is going to be equal to 1. On the other hand, if I have calcium silicate, there, okay, the activity of silica is going to be substantially smaller because the silica is in a bound state. Okay? So, therefore, the activity of silica is going to be substantially less in the presence of a calcium silicate sag, and in that case, if we look at the deoxidation reaction, okay, we can say that, well, lesser is the activity, I am writing it in simple form, okay, MO, I can say that lesser is the activity of MO, more is going to be the efficiency of deoxidation reaction, or lesser is this reaction will be moving Lesser activity means as if we are continuously removing the product from the site, and as a result of which the reaction will have more spontaneously proceeding towards the forward direction itself. So, therefore, we understand that simple deoxidations are less efficient than complex deoxidation, and as a result, as a matter of fact, in steel plants if you go, you will see that the deoxidation is taking place not only by aluminum, but we are adding some silicon also, some ferromanganese also, some aluminum also, and aluminum by far is the most powerful deoxidizer. So, a substantial amount of deoxidation will be carried out by aluminum itself, but not necessarily all deoxidation will be carried out by entire deoxidation will be carried out or facilitated by aluminum. We will be adding some silicon, ferrosilicon or ferromanganese also along with aluminum. Now, coming back to the deoxidation product again, as I have mentioned that the deoxidation products are forming where? The deoxidation products are forming, be it liquid, solid or gas, it is going to be forming in the bulk of the liquid, because it is here that the metal is going to come in contact with oxygen, and it is here the deoxidation product is going to be formed. So, we do not want these deoxidation products to be entrapped in the molten steel itself. There is a necessity that these deoxidation products actually go out of the melt and float in the slag, which can be eliminated suitably during the falling process itself. So, we want steel which is free from contamination by the deoxidation products. That is an essential requirement. At no stage, and particularly in the final stage, we must not have even a little bit of the deoxidation product which is there in the steel, because it is well known that deoxidation products are going to hamper the mechanical properties of steel. So, if you have solid deoxidation products, for example, the solid deoxidation products, they do not, the one solid deoxidation product can form here, the other can form here, but the solids do not collide. Okay? And these deoxidation products are basically lighter particles, so they naturally have a tendency to float up to the melt. Okay? But one important thing is that these deoxidation products, if they are solids, in that case they do not tend to form bigger masses. On the other hand, if we have liquid deoxidation products, in that case the liquid deoxidation products, if they come together, then immediately they form a bigger particle. Okay? And as you all know that a smaller particle will have a smaller rise velocity, and a bigger particle will have a lot of rise velocity. So, the bigger we would like to have bigger particles, and therefore, if we trace back, we would say that a liquid deoxidation product is perhaps more desirable to us than a solid deoxidation product. Interestingly, aluminum has the largest affinity towards oxygen, most powerful deoxidizer, the least level of contamination, but this aluminum is going to give us a deoxidation product that is essentially solid in nature. So, there the contamination of steel with Al2O3 is a major issue. Lot of alumina particles can be entrapped, and this tends to make what is known as a dirty steel. Okay? So, in this particular case, we can have the point that I have made, that alumina particles or the solid particles, smaller particles will rise slowly, and bigger particles are going to rise faster. We can use the Stokes settling velocity or rising velocity, and we can say that the terminal rise velocity is actually g diameter particles square into delta rho divided by 18 mu. So, I am not saying that this equation does hold good all the time or for all size ranges, but it gives us some idea and tells us that the rise velocity is going to be directly proportional to the square of the diameter. If you increase the diameter by a factor of 2, the rise velocity is going to be increased by a factor of 4. So, therefore, once the ladle is filled up here, okay, and you are taking it to subsequent stations, you get some time, and in that particular time what happens, the deoxidation products which have formed deep inside the system, they have a chance to float up. So, you have to give sufficient time also for these inclusions to float up to the free surface or the surface where we have slags already forming, and these slags can capture the deoxidation products. I must also tell you one important aspect, that because there is going to be some stirring, so the deoxidation products can rise to the slag metal interface, but at the same time, because of the stirring present, this deoxidation product can be re-entrained back into the steel also. Okay? And typically, the deoxidation products rise to the slag metal interface, and the slag captures the inclusion. The slag removes this non-metallic inclusions or harmful inclusions, but the inclusions really stay for some amount of time in the vicinity of the slag before they are going to be completely captured by the slag itself, and this is basically referred to in steel making reactor as the dwell time of the inclusions or the dwell time of the deoxidation products. Okay, they have to dwell in the vicinity of the slag for some amount of time before being completely captured by the slag layer itself. It is important for us that the metal be free of, molten steel is free of such deoxidation products. We must, and the secondary steel making or ladle metallurgy steel making, as we will see, as the processes go on and we generate more and more deoxidation products as a function of time, our one of the major thrusts would be that if there are inclusions particles present in the melt, how to drive them out, how to produce clean steel, which is a very important issue, pertinent issue. Okay, we do not want dissolved impurities, we do not want much sulfur, we do not want oxygen. Okay, we do not want nitrogen, we do not want hydrogen. At the same time, we do not want this unwanted non-metallic inclusions as well in the steel bath itself. So therefore, as a coming back to the Stokes law of settling, I would say, given the size range, and if I know the bath height, I should be able to find out, what is the possibility of inclusion, okay, flotation. We can calculate and show that if the inclusions are of the order of 40 to 50 micron size, they virtually have no possibility to rise up and float to the free surface. On the other hand, if the inclusion size is 200 or 500 microns, for example, in that case their rise velocity is going to be so large that in 1 to 2 minutes of time they should be able to cover the entire depth of liquid and come up with the slag metal interface where they can get absorbed. Okay. Of course, Stokes law, it's a very simple law. We all know that it is valid for laminar flow. Even Reynolds number of the order of 1, very quick kind of a flow, which is typically very weak quick flow. And in this particular system, we know that it's there's a fluid motion also. It is not the particle rising through the stagnant bath. Also, the surface tension in high temperature systems are different. The particles may completely wet, may not wet. So this is an approximate order of magnitude calculation. These need not be taken too seriously. We just get some idea that what size of inclusion can float and what size of inclusion cannot float, and nothing beyond that. No serious process design calculations or inferences should be drawn on the basis of the Stokes law as far as the inclusion flotation is concerned. So before we proceed further, I also want to say that or draw your attention to one fact, that if you have noted so far that this is the solid has added solid has dissolved into steel, or oxygen is already dissolved in molten metal. They collide with each other, okay, they come together, react with each other because of their affinity, and now this is a product which is altogether new phase. Okay, for example, you have steel, and then you can visually distinguish that alumina particles have formed. So a new phase has formed, and therefore if you apply our knowledge, that we must understand that the formation of a new phase is always accompanied by what is known as nucleation and growth. So in deoxidation, various complex phenomena are involved, and I can tabulate them as a diverse kind of a. So dissolution, and then following by that the new phase is nucleated, the new phase is grown, okay, and then subsequently the new phase has floated, and this totally constitutes the kinetics, various kinetic aspects of the deoxidation process itself. Now I don't want to talk anything beyond this as far as deoxidation is concerned. I think in the next lecture I am going to show you a deoxidation calculation, but to sum up today's lecture and give you an overview of the deoxidation process, I must say that we have primary steel making. The bath is rich in oxygen. We got to remove oxygen from the bath, and because we know that oxygen is going to, if it remains, there's so much of oxygen during the solidification, oxygen is going to be evolved because solid has less solubility than liquid. So the oxygen present in steel is going to impair the mechanical properties. So before we process steel further, we would like to take out oxygen first. Okay, there are other impurities also present in metal, but we are going to talk a little bit later about them. And when we want to take that oxygen, remove that oxygen from the bath, we realize that we have to now add an element, okay, which has a greater affinity towards oxygen. And that we wish to remove oxygen from the bath, we make it sure that the oxidizing slag from the BOF or the carryover slag does not come to the ladle at all. most commonly used deoxidizers are aluminum, silicon, ferrosilicon, ferromanganese, silicomanganese, etc. If you use one single element to deoxidize the bath, it is a simple deoxidation. If you use two elements or more than two elements simultaneously, it is a complex deoxidation. And I have shown you that the efficiency of complex deoxidation is going to be greater than that of the simple deoxidation. Aluminum by far is the most commonly used deoxidizer element in steel. Deoxidizer elements are basically lighter than that of steel. So, therefore, when you make bulk addition into the ladle, we will try to target them near the falling stream where the velocities are extremely downward, okay, or highly downward, and this downward flow of steel can really take the deoxidizer elements along with it, a subsurface where subsurface melting and dissolution can take place. Now, once the deoxidizer element gets into the bath, it melts and dissolves. Once it dissolves, it reacts with oxygen. So, it is a mass transfer process, because oxygen has to go and find out a metal, dissolved deoxidizer element. Dissolved deoxidizer element has to find an oxygen atom, and that is how they can collide and form a new phase. So, therefore, this is the mass transport step, and therefore, we need some kind of a stirring. That stirring is initially provided by the convection generated by the falling stream, or alternatively, when the intensity dies, we have gas injection, which is always being used, and that gas injection gives rise to stirring, and which basically aids in the deoxidation process itself. We have solid deoxidation product, liquid deoxidation product, gaseous deoxidation product. Solid is not wanted, as far as possible, but we see that aluminum, which is such a powerful deoxidizer, which gives low residual, can bring down oxygen to a very low level with little bit of contamination only, unfortunately forms a solid deoxidation product. And we want that final steel has to be devoid of these deoxidation products, which we call later on, as we will know, is inclusions, and contamination of steel with deoxidation product is basically, referred to as dirty steel. On subject, associated subject is the cleanliness control, and so on. So, kinetically, we can assess the process of flotation of inclusion by adopting Stokes' law, and as I said, that once it dissolves, then the nucleation, because the new deoxidation phase has occurred, and that nuclei has to grow, and once it grows, it then floats, okay, and flotation of the inclusion is a very important aspect. And as I have also finally, towards the end, I have mentioned that the inclusions will float, collide first. They can collide with each other if they are liquid. Gas is no problem. Gas is very light, so immediately they will move out. So, once they come to the slag metal interface, we can say that they can dwell there for some time to be ultimately captured by the slag itself. So, I conclude here today's lecture, and in the tomorrow, I think I am going to show you, or in the next lecture, I am going to show you how to perform a deoxidation calculation, with exact data.